This video is part of the lectures related to the machine dynamics topic. It is the first video of the introduction section. This video is going to introduce mechanisms or linkages. By the end of this video, you will be able to first, recognize links, that essential parts of mechanisms. Second, you will be also able to recognize kinematics pairs or joints, that are connections between links. Then, you will be able to recognize mechanisms, which are specific arrangements of links and kinematic pairs. Next, you will be able to give some examples of mechanisms. Last, you will be able to give some applications of mechanisms, in real engineering solutions. To achieve the learning outcomes enumerated previously, the video is divided in 4 parts. First, we are going to define what are mechanisms. We are going to focus on the useful definition of mechanisms and not recalling the historical definitions. It will not be able to understand what is a mechanism without having a deep understanding of links, kinematic pairs, and kinematic chains. Thus, in the second part of this video, we are going to define what are links, kinematic pairs, and kinematic chains. Then, we will give some examples and some applications, in the third and fourth parts, respectively. Examples will help you to have a feeling about the definition of mechanisms. You will be able to recognize which mechanical system is a mechanism and which is not. Applications will give a feeling about the usefulness of mechanisms. Let's start with the first part. In this part, we are going to define what are mechanisms. Namely, we are going to give a useful definition of mechanisms. A definition that will help in differentiating mechanisms from other mechanical systems. A mechanism is a mechanical system that is made of links or rigid bodies. Rigid bodies or links are mechanical parts that conserves their shapes while moving or subjected to forces. The distance between any 2 points, of a link or a rigid body, remains always constant and does not change. Angles within a rigid body, or a link, also does not change. In a mechanism, the links are assembled or connected together, using joints, or kinematic pairs. The kinematic pairs are contact points, lines, or surfaces, between links, that reduce or block some relative degree of freedom. These two conditions build a kinematic chains. A kinematic chain is assemblage of links using kinematic pairs or joints. In a mechanism, we should also have a link, considered as a reference for mechanism's motion. This link is also called the ground or the frame. A mechanism is a kinematic chain having a grounded link. The ground or the frame is not necessarily a static non-moving link. It is rather a link that is considered as a reference for the mechanism's kinematics. In other words, the kinematics of the mechanism is studied, relatively to the link, which is chosen as a reference or the ground. A mechanism receives an input motion. This means that one link, or more, will be controlled by an external source of energy. In response to this input, the mechanism will move in completely determined and controlled way. The output is the motion of one link, or more. A mechanism is a kind of motion transformer. It receives an input motion and it gives back another output motion. A simple and common example of a mechanism is the 4-bar mechanism. In this mechanism, the links are 4 rigid bars. As the bars are rigid, their lengths are constant. The 4 bars are connected together using 4 revolute or pin joints. Pin joints allow only relative rotation between links. Thus, the bars can only rotate relatively to each other. No relative translation is allowed. Now, we have a kinematic chain. To make it a mechanism, one link should be considered as the ground or a reference. The motion analysis will undertaken assuming that the reference link is static or fixed. The kinematics of other links will be considered relatively to the reference or grounded link. In this example, link 1 is considered as the ground link or the frame. The motions of links 2, 3, and 4 are determined relatively to link 1. A mechanism transforms an input motion to another output motion. Here, for example, the mechanism transforms a crank motion, full rotation motion, of the input link 2, red link, to a rocker motion, back and forth rotation motion, of link 4, the cyan-colored link. The input link is driven by an external source. Once, the input link is controlled by assigning a desired input motion. The other links, and mainly, the output link, move in a controlled and predictable way. A mechanism involves links and kinematics pairs. A mechanism is a special type of kinematic chain, where one link is considered as the ground. Thus, in the next part, we are going to focus, with some more details on links, kinematic pairs, and kinematic chains. A link is a part or an element of a mechanism that can be assumed a rigid body. Rigid bodies are mechanical elements that do not suffer any change of shape. A body can be considered as rigid body, if the distance between any 2 points of that body remains constant or does not change while the body moves or subjected to a load. A rigid body does not suffer a distortion of shape. The body's shape is then conserved. As a rigid body, a link can translate, rotate, or combine translation and rotation. Translations and rotations are the only transformations that conserve distance, angle, and shape. In planar mechanisms, each link has 3 degrees of freedom, 2 translations, the horizontal and the vertical, and 1 rotation. Any other motion of a link is a combination of the 2 translations, a combination of a translation and rotation, or a combination of the 2 translations and rotation. Any body, subjected to loads, or accelerations, suffers some distortions. However, in mechanisms the distortions of links is insignificant, and it does not affect their kinematics. Thus, the link's distortion can be neglected. That's why links are assumed to behave as rigid bodies. For example, the gear teeth, when meshed, suffer some distortion. However, the gears should be designed such as this distortion remains insignificant or negligible. Also, in a cam and follower mechanism, both cam and follower suffer some distortions. The mechanical designer should keep these distortions within an acceptable range. That does not affect the cam and the follower kinematics. A link is not necessarily built or manufactured in one part. A link can be made up of several parts. However, in a link, all parts are all tightly assembled together. Or, they are assembled such as no relative motion is allowed. Thus, all parts behave as one whole rigid body. For example, 3 bars that are connected together by 3 pin joints build a structure that does not allow any relative motion. It can be considered as one link. Also, in an automobile engine, crankshaft, crankpin and flywheel are manufactured separately. However, they are assembled tightly such as no relative motion is allowed. Hence, they can be considered as one link. The shape of links rarely affect the kinematics of a mechanism. Studying the kinematic of a mechanism is mainly based on the kinematic diagram of a mechanism. Kinematic diagrams rarely pay attention to the link's real shape or geometry. It focuses more on relative position of connections or joints. A 4-bar mechanism is not necessarily built up from rod-shaped links. The bars are kinematic representation of binary links that rotate relatively to each other. Behind the kinematic diagram of a mechanism, there is a real shape for each bar. However, the most important is the nature of joints and their relative position. Let's have some example of links. However, we will focus only on planar motion or links that can be used in planar mechanism. Binary links, represented as bars, they can have any shape. However, a binary link is connected to at least 2 other links using pin joints. Thus, it can rotate relatively to the 2 links it is connected to. The line, or the bar, links the 2 pin joints. Ternary links are represented as triangles. They can also have any shape. A ternary link is connected to at least 3 other links using 3 pin joints. It can then rotate relatively to the links it is connected to. Quaternary links are represented as quadrilaterals, independent of their real shape or geometry. A quaternary link is connected to at least 4 links, using 4 pin joints. Sliders are represented as rectangles in kinematic diagrams. A slider is translating relatively to another link. Gears are teethed links. The most common are spur gears. Cams are links that drive other links through direct contact. A joint or kinematic pair is a contact between 2 links that limits or reduces the relative degree of freedom. The contact making the joint or the kinematic pair can be a point, a line, or a surface. Joints or kinematic pairs are used to assemble links together. A joint or kinematic pair limits the degrees of freedom. Without a joint, 2 links move independently of each other. In planar motion, one link has 3 degrees of freedom relatively to another link, 2 translations and 1 rotation. Using a joint or kinematic pair reduces the relative degrees of freedom down to 1 or 2. For example, one bar, the right bar, can translate horizontally, can translate vertically, can rotate relatively to another bar, the left bar. Using a pin joint, the right bar can only rotate relatively to the left bar. However, the right bar cannot translate any more with respect to the left bar. The 2 relative translations are blocked by the pin joint. Thus, kinematics pairs are used to assemble links together. Without kinematics pairs, the links are dismantled from each other. They move independently of each other. Using joints or kinematics pairs, make links work and move dependently. The motion of one link affects the motions of the others. In the example on the top, the bars are assembled together due to pin joints. In the example in the bottom, there is no kinematic pairs used. Thus, the bars are dismantled or disassembled. Each bar can then translate or rotate independently of each other. Assembling links using joints or kinematic pairs builds a kinematic chain. Thus, a kinematic chain is the assemble of links using kinematic pairs. Let's have some example of links. However, we will focus only on planar motion or links that can be used in planar mechanism. The first example is the pin or revolute joint. The pin joint blocks the two relative translations. Links can only rotate relatively to each other. Each link can rotate independently of each other. The rotation speed and direction of one link is independent of the other link's rotation speed and direction. Prismatic joints connect two links by cancelling the relative rotation and one relative translation. Thus, one link can only translate in one direction relatively to the second link. It is possible to have one link translating and the other static. Or also, it is possible that the two links translate. Cam joints are obtained by simple or direct contact between two bodies or links. Cam joints allow one translation and one rotation. Gear joints are obtained by contact between teethed bodies or links. Gear joints also allow one relative translation and one relative rotation. The joints or kinematic pairs can be classified in lower and higher pairs depending on the type of contact. Lower pairs are joints with surface contacts between links. In planar motion, pin joints and prismatic joints are the only lower pairs. Higher pairs are joints with point or line contacts between links. Cam joints and gear joints have line contacts. Thus, they are higher pairs. Kinematic pairs can also be classified depending on the number of degrees of freedom they allow. 1 degree of freedom pairs allow only 1 degree of freedom. Pin joints allow 1 rotation, and prismatic joints allow 1 translation. Both are then 1 degree of freedom pairs. In planar motion, two-dimensional motion, all lower pairs are 1 degree of freedom pairs. This is only true in planar motion. It's not true in space motion or three-dimensional kinematics. Two degrees of freedom pairs allow two relative degree of freedom between links. Cam joints and gear joints allow one rotation and one translation, they are 2 degrees of freedom pairs. Also here, and only in planar motion, the higher pairs allow 2 degrees of freedom. The order of a joint depends on the number of links they are connected through that joint. A joint is of order 1 if it connects together 2 links. A joint is of order 2 if it connects together 3 links. A joint is of order p if it connects together p plus 1 links. The order of a joints is the number of links connected by that joint, minus 1. After having a detailed description of links and kinematic pairs, we are now ready to have some examples of mechanisms. Just before giving some examples, we need first to introduce kinematic diagrams. Kinematic diagrams are simple, clear schematics of mechanisms. Kinematic diagrams does not show the real shape or geometry of links. Kinematic diagrams pay more attention to the joints and their relative positions. Here are some simple representations of joints or links. The 4-bar mechanism is the most common mechanism, for its simplicity. It is built up from 4 links connected with 4 pin joints. The links are the ground, the input, the output, and the coupler. The input can be crank or rocker. The output can also be either a crank or a rocker. A second example is the slider crank mechanism. It is also made up from 4 links, the ground, the crank, blue link, coupler, magenta link, and slider, red box. The links are connected through 3 pin joints and 1 prismatic joints. The slider translates along the ground or reference link. The crank, blue bar, rotates relatively to the reference link. The input can be the crank, in that case the output is the slider. The input can also be the slider, thus, the output is the crank. The slider crank mechanism converts a rotational motion to a reciprocal motion or vice versa. The third example is the Scotch yoke mechanism. It has also 4 links, the ground, a bar, and 2 sliders. It converts a rotational motion to a reciprocal translating motion or vice versa. Another example, involving higher number of links, is the 6-bar mechanism. It uses 6 links, 4 binary links and 2 ternary links. Any link can be considered as the ground. Here is a simple example of an ordinary gear train made up from 3 spur gears. Here the mechanism uses 4 links, the ground is the 4th link. After giving few examples of mechanisms, let's see some applications. Any device or machine that moves, or have a subsystem moves, contains one mechanism or more. A bike, for example, employs a mechanism to transform the feet motion of the rider to a rotation motion of the rear wheel. The mechanism uses a crankset, a chain, and a cassette. It provides a torque or speed multiplication. An automobile involves several mechanisms. The gearbox is an example of these mechanisms. Manual transmission systems use compound gears trains to provide torque multiplication. Also in a car, the gas engine uses slider crank mechanisms to transform the reciprocal motion of the piston, induced by the gas explosion, to a rotational motion. Construction equipment, fitness equipment, robots, involve many mechanisms. Mechanisms are around us, in almost all machines. Their application is wide and versatile. We come at the end of this video about an introduction to mechanisms, links, kinematic pairs, kinematic chains, and their applications. Thanks for watching.